Well, hello again. In this example, you will learn how to generate a set of superimposed moment diagrams for a beam. We're going to look at this multi-connected beam, and we are being asked to use the principle of superposition. Whenever we do that, we need to have a place that we're going to cantilever. So specifically, we're being asked to cantilever at point C. Once the diagrams have been created, we're asked to verify that we have done it correctly, and we will do that by summing up the moments on each side of the cantilever. Make sure they do sum up to be 0. So let's go ahead and get started with this. We've provided the reactions for this already. If those hadn't been provided, you would need to solve for the reactions first. So principle of superposition says choose a point to cantilever. I will cantilever at point C. Now conceptually, I want you to think of it like this. Point C is cantilevered, and then go ahead and treat each beam or each load as a load that acts on a cantilever beam. So I'm going to go ahead and sketch something like this. We will get a load of 9 kips right here. Don't let this negative sign confuse you. That negative means that it is acting in the downward direction. So we've got that done appropriately. We've also got another cantilever beam here that has a load being applied to it of 24 kips. On the right side of the cantilever, we've got a beam here that has a distributed load. We've got a beam here that has a point load of 15 kips. And I guess that distributed load, if you want, you can write 2.5 KLF. And then we've got a cantilever beam that has a moment here of 120 kip feet. Now, one concern that tends to arise here is when you sketch those cantilever beams, you say, wow, you know, there was a moment release here. Why are those not showing up in here? Let me just assure you that that moment release, the way it showed up, or the way it was handled, was in the computation of the reactions. Now, if you've gotten the reactions correct, everything else that we develop here will be correct using the principle of superposition. Well, so from here on out, what you really want to do is go ahead and generate moment diagrams for each of these individual loads and individual beams. And that is what these superimposed moment diagrams actually look like. This is where it is very nice to have moment diagrams for these simple cantilever beams memorized. So we will kind of clip through this fairly quickly, handling the point load out at point A first. We will be generating these moment diagrams using units of kips and feet. So I'll try to highlight this. I'm going to do this one first, and we will plot it here. Recognize that this is the point of cantilever. Okay, so for a cantilever beam with a point load out on the end is 0 on one end, and it is nothing more than that load, 9 kips multiplied by the moment arm of 16 feet. That will be negative 144. And it'll be a straight line for the point load. You can see this in any textbook, or you can verify it on your own that this is the way it is. But remember, the real strength in the superposition method is to have these shapes of the moment diagrams memorized already. So we come back here, and we're trying to do it for this beam. So think of it as being a point load out on a cantilever beam. It will create a shape here of 144, and that is 24 times 6. Gives me 144. And so what we're going to notice right now is that those do sum up to be 0, which we know in the real structure the moment here is going to be 0 simply because there's a pin. But we're not done. We need to go ahead and handle the others here. So let's handle this one next. That one is a little bit more involved, but not too much. I'm going to remind you that this is the point of cantilever, and that we are working in units of kips and feet. So the memorized shape for this is at the end of the distributed load is 0. It's a second order curve. It becomes something like this. The only thing in question is this magnitude, which is negative 180. And the way that is gotten is it is computed as WL squared over 2. Once again, this is found in the textbook. So this is 2.5 is the load. The length is 12 feet. Divided by 2, that'll come up to be negative 180. And that will be a second order curve. Next one we want to handle is going to be that point load. So it's another cantilever beam. So it'll be a triangular moment diagram. That'll work out to be 300. That would be 15 times 20. That's a first order curve. And last but not least, we've got this cantilever beam with an applied moment on the end. And that creates a uniform moment diagram here. So this is negative 120, negative 120. So these are our superimposed diagrams, and if we've done this correctly, these things should sum up to be equal to 0. And in fact they do, so we feel quite confident in the calculations that we have made. And we do not superimpose the actual diagrams. Any work we do with these diagrams will be done in this particular form. This concludes this example, and as always, it's a beautiful day for studying structures.